property. So scaling down or transistor scaling beyond certain dimension in planar technology now impossible. So we need to find something else to make it more smaller and to make it faster.
Is there any kind of doping technology that we could use that would?
We have all sorts of doping engineering. It's called device engineering. That has been tried. Every possible doping technology and other material level optimization has been tried, because now it's all about physical dimension. Because every silicon atom has a physical dimension. When you make it silicon dioxide with a silicon 2 oxygen, it has a physical dimension. If you reach, you need to have at least several hundred atoms side by side to reasonably form a layer, right? So that's why. So initially started with planar MOSFET, and then they introduced a variation of planar MOSFET. It's called SOI technology, silicon and insulator, SOI technology. And then they recently, around 2012, Intel introduced FinFET. The FinFET technology is like in the planar technology, the gate or the channel area is in the same plane, that's why it's with the body itself. In FinFET technology, here is the body and the channel is rising above the body, a silicon tower or fin like a fish. That is called FinFET technology, and it improved performance and scalability significantly. At one point, they already determined that FinFET technology will reach its limit. Then they are now exploring negative capacitance-based field effect transistor. And then the next one is completely get away with field effect transistor technology. A new technology will be introduced, band-to-band tunneling. So there is another option. Or if we want to remain in FET technology, nanowire-based device, that is another option. And then beyond this FET technology, band-to-band tunneling technology, if we want to completely move out of this conventional transistor technology, new type of device based on magnetic torque. That is something is being explored. And further futuristic approach is called memristor. So these are just one slide to show you the progression of technology and the future direction, where it is going in future. And in terms of material, silicon will become obsolete at one point, or will not be able to provide extremely high density and high performance, high speed application. So people are also exploring different types of nanomaterial as an alternative to silicon. One group of nanomaterial is known as 2D nanomaterial. Among those, most famous is graphene and carbon nanotube, 2D nanomaterial. And the third one that is becoming popular nowadays is molybdenum disulfide as an alternative to graphene, because graphene has some limitation. And then completely new class of nanomaterial for magnetic device and ferroelectric device. People are exploring ferroelectric and ferromagnetic material for not electronics, for magnetronics or magnetic spin-based device. These are the new class of material people are exploring. Just this for information only. And this I already mentioned, the progression of device, the technology. So now let's move to our lecture 2. This is where we will start talking about semiconductor material and semiconductor device. So in this lecture, we will be first looking at the basic building blocks of any integrated circuit. We will do some revision of fundamental material or semiconductor concepts, and then we will discuss at length in detail on MOSFET device, its operation and design. So if we look at any electronic circuit, including integrated circuit IC, it is made of several components. Number one, the device. The device for signal processing. Any electronic circuit needs some active device for signal processing. And the most common active devices are transistors and diodes for signal processing. And what is the materials for device? Currently, the two predominant semiconductor material used for those devices are silicon and germanium. Silicon is the main and germanium is used for some power electronics device. The second component or building block of IC is interconnecting wires to connect all those transistors to form the circuit. Typically, interconnecting wires must be very good conductor, and conductors are made of mainly metals. Two of the most popular and widely used conducting metals for interconnecting wires are copper and aluminum. And the third component of integrated circuit is contact. A contact is a connection between semiconductor device and metallic interconnect. One thing you have to understand, when you join two different types of material, it is not easy to make the connection, physical and electrical connection, because you are having a silicon material which is not very tensile or it doesn't have good conducting property, and metal, it is easy to do soldering and connect it, right? Metal to metal contact. But metal to semiconductor contact is not very easy because their material property and physical properties are completely different. So you need an intermediate set of material to provide stable physical connection between semiconductor and interconnect, also stable and reliable electrical communication between semiconductor device and metallic interconnect conductor. Those are called contacts. So, and the fourth component is also another contact, but it is known as vias. Vias are vertical connection between interconnect lines in two different layers. So in one of the microphotograph we have shown that there are layers of interconnecting wire inside IC. You need multiple layers of interconnecting wire to connect billions of transistors. So if you have one wire in layer number 7 and another wire in layer number 2, together they are connected to a certain transistor, you need to provide a vertical connection from layer 2 to layer 7. Those vertical connections from one metallic line to another metallic line, that connecting points are called vias. So vias and contacts, they are the same thing, providing connections with one component with another component of IC. However, the term in semiconductor terminology, the term contact is reserved for connection between semiconductor to metal. The term via is reserved for connection between metal to metal. So and then the fifth component of any integrated circuit is insulation layer. Wherever you don't need any connection, you have to fill the gaps with insulation layer so that you don't get unintentional short. Or you need to hold those devices and interconnect in its place when you form the circuit. So for physical placement and electrical isolation, you need to fill all the gaps in between ICs, interconnects and transistors with insulator. That is the fifth component of IC, and typically the most common insulation material used in integrated circuit is silicon dioxide. So these are the 5 major components inside the IC and the material used for those components. Now, so from this discussion, what we can see that the main functional component of any IC is the semiconductor device, transistor and diode. They will do all the signal processing activity for you, whether it's a microprocessing, whether it's a memory information storage. All these things, the basic functions of any electronic system, signal processing and signal storing, both will be done by semiconductor device, and majority of the IC semiconductor devices are made of silicon. Only small portion is made of germanium or any other semiconductor. So we need to know the basic property. A quick recap of silicon. Why silicon behaves like a semiconductor. First of all, what is a semiconductor? Material can be grouped into three groups: conductor, semiconductor, and insulator. Conductor, when you apply electrical field or voltage across the conductor, it can carry current very easily. It's conductor. Why it can carry current very easily? Inside the metallic conductor, there are lots of free electrons available. First of all, what is electricity? Flow of electrons. Electricity or the current is flow of electron. So to have good conductance, to have more currents, what do you need? You need more electrons. Metallic conductors inherently have more free electrons available inside any metal sample. So if you apply a voltage, there will be a high current because it's a conductor. Semiconductor, in its pure form, has very small amount of, negligibly small amount of free electron. So they don't conduct that much current. But if you dope it or if you excite it some way or the other, it can carry a finite amount of current as long as that doping or excitement is present. If you remove the doping or that excitement, then it cannot carry any reasonable amount of current. So that's why it is a semiconductor. It achieves conductance or ability to carry current with some conditional situation. That's why it's called semiconductor. The third group is insulator. It will prevent any flow of current. It's called insulator. So the most popular and widely used semiconductor for IC industry is silicon. Silicon is a group 4 material. Now let's quick recap of chemistry 101. In periodic table, any material in group 4, behind you, the periodic table on the wall, there is a periodic table here, right? So group 4, silicon is a group 4 material. That means in its outer orbit, it has 4 electrons. Another chemistry 101. For any chemical component on a material to achieve stability, chemical stability or material stability, it needs to achieve 8 electrons for all the material except hydrogen. For hydrogen, it needs to have 2 electrons. So for all the material, every silicon must achieve 8 electrons altogether to have a physical and material stable state. So now, every silicon has 4 electrons in its outer orbit. If it can share another 4 electrons with 4 of its neighbor, so it will have in total 8 shared electrons. 4 from itself and 1 each from 4 neighboring silicon atom. So the sharing of electron with neighboring atom, it is in chemical term, it is called a covalent bond. So every silicon atom will form covalent bonds with 4 neighboring silicon. In the process, as a result, it will achieve strong physical and material state. From electrical point of view, these covalent bonds are very strong. So all the electrons in the outer orbits of silicon, they are held with the atoms of the silicon very tightly, very strongly due to the presence of covalent bonds. But to carry current, to send electricity through silicon, we need to free up those electrons, right? So, in its pure form, silicon does not have that much free electron. That's why it is not a good conductor. But if we apply some chemical process called doping, we can increase the number of free electrons in the silicon sample, so it will give us some finite amount of current with certain chemical modification. Or with some voltage application we can do that, and that's why it is called semiconductor. Now let's see what is the atomic density of silicon. Atomic density of silicon is 5 times 10 to the power 20. That means in 1 cubic centimeter or 1 cubic volume of silicon material, there will be 5 times 10 to the power 20 atoms. So, in conductor, metal, every metal atom will contribute at least 1 free electron. So, inside iron, aluminum or copper sample, per cubic centimeter sample will provide 3 electron, one electron by one atom. But now let's see what happened to the silicon. In silicon, the actual number of free electron that is available per cubic centimeter is in the range of 10 to the power 10. But in per cubic centimeter, we have almost 10 to the power 25 times this much atom. So that means for every 10 billion silicon atom, you are getting only 1 free electron. This is the electron density, is called charge density, electron density in pure silicon. It is per centimeter cube. That means we will have this many free electron for every cubic centimeter volume of pure silicon. But in pure silicon, that many atoms are there. If you compare this one with this one, it will be like 5 times 10 to the power 12, right? 10 to the power 9 is 1 billion, right? Or 10 to the power 12 is 1 billion. So, that for that many silicon atom, you will have only 1 free electron. That's why it's very, very poor conductor. So now, to have any reasonable amount of current, you have to make those electrons or force those electrons to be displaced from its orbit. Because inside its orbit, they are very, very strongly held by covalent bond like this. So this dotted line here, this line, it shows that covalent bond. Every electron is covalent, strongly held in covalent bond. So to force current through silicon sample, we have to displace an electron from its orbit. If we can displace that electron from its orbit, it becomes free. That means free to move. But by displacing an electron from its orbit, what we are doing? We are creating a gap or hole in its orbit. So every electron, by default, carries 1 unit of negative charge. Every electron, it is a fundamental particle of any material. Every electron contains 1 unit of negative charge. So, typically, any silicon atom is by default charge neutral. That means the number of negative particle in its orbit, electron, is exactly equal to the number of positive particle, proton, in its center or nucleus. So overall, silicon atom is charge neutral. So if you push one electron out of its orbit, it leaves a gap or hole. That means overall this atom has become positively ionized because it lost one negative particle. So this gap and hole is a virtual particle, and it is known as a hole, and it is assumed to be a positive virtual particle. So every time in a silicon atom you can free up, you can make an electron free, then you get a free electron, that is one negative particle, to move to produce electricity, but in the process it creates a virtual positive particle or hole, in the atomic orbit. So inside pure silicon, every time you create a free electron, you also generate a positive hole, which is a virtual positive particle. So electron and positive hole, negative electron and positive hole, they come in pair, and it is called electron hole pair. So inside semiconductor, flow of electricity or flow of charge will take place due to the creation and movement of free electron and due to the creation and movement of virtual positive charge particle hole, which is slightly different from metal. In metal, there will be no hole created. There will be lots of free electron readily available. So through the metal, electricity or conduction of current is due to the movement of electrons only. There's a difference of conductance in metal and conductance in semiconductor. In metal, flow of charge or electricity is due to the movement of free electrons only. In semiconductor, charge conduction or electricity will be due to the movement of free electron in this direction, so hole will move in the opposite direction. So as I said, they will come in pair. So in pure silicon sample, if you do not add any foreign material, every time you create a free electron, it will generate a hole, so they will come in pair. So if you create 1 million free electrons, it will give you a 1 million hole. And that density in room temperature, for pure silicon is called intrinsic carrier density. And the symbol is Ni, intrinsic carrier density. And this intrinsic carrier density Ni tells us at room temperature in pure silicon form how many free electrons and how many holes will be there. And that number per unit volume is called carrier density or intrinsic carrier density. So this one already explained that current conduction in silicon or semiconductor is due to the flow of electron and flow of hole. If electron moves in this direction, hole will move in the opposite direction. So in pure silicon, that intrinsic carrier density Ni, typically as I mentioned, is in the order of 10 to the power 10. That means this is per cubic centimeter. That means for every cubic centimeter silicon sample, there will be that many free electron and hole, negative and positive hole. So this is called intrinsic carrier density. So just without knowing exact silicon atomic density, this looks like a very big number. So you may erroneously think that, well, then silicon should be a very good conductor, but you have to compare for how many silicon atoms. Silicon atomic density is in the range of 10 to the power 22. So every several hundred billion silicon atom, there will be only one free electron. So it is a very, very poor conductor. So silicon in pure form is a very poor conductor because it doesn't have enough free electron or hole to contribute to producing any reasonable amount of current. So that's why we have to change the material composition or material property of silicon as a semiconductor to be used in any real circuit application. So silicon in its pure form is called intrinsic semiconductor. Any semiconductor in its pure form is called intrinsic semiconductor. And it is a very poor conductor because it doesn't have enough charge carrier, free electrons and holes to current. So its conductivity cannot control because it is a very poor conductor. On the other hand, if we mix some specific foreign materials with silicon sample, some material has the ability to donate some extra free electron, and some materials have the ability to donate some extra hole positive particle, so it will increase its charge density. And the process of mixing foreign material with pure silicon to increase electron density or to increase hole density is called doping. And the resulting silicon sample, which is doped, also is known as extrinsic silicon or extrinsic semiconductor. So now, as I just explained, mixing chemically a foreign material, it can lead to increase of electron density or increase of hole density. Electrons are negative, holes are positive charged particle. If any doping process results in a silicon sample with more electrons, we call it n-type semiconductor. If any doping process results in more hole in the silicon sample, there is more positive particle, we call it p-type semiconductor. I know many of you have taken semiconductor device course, so I'm just quickly going through this to mainly remind you about the basic concepts and definition. As I mentioned earlier, in its pure silicon form, there will be low number of free electron and hole, and however there will be some finite number of free electron and hole. They come in pair, equal number of free electron and equal number of hole, and that density of electrons and hole in pure silicon is called intrinsic carrier density, and as you can see the number is in room temperature 1.45 times 10 to the power 10, whereas the atomic density is 5 times 10 to the power 12. So in its pure form, electron density in pure silicon is equal to hole density in pure silicon because they will come in pair. And that will be equal to intrinsic carrier density Ni, which is 1.45 times 10 to the power 10 at room temperature. It is interestingly, the device physicists observed that by doping process, what you can do? By doping process, either you can increase electron density or you can increase hole density. So by n-type doping, you increase electron density. By p-type doping, you increase hole density. But it is observed that at any given point, in pure form, intrinsic form, or extrinsic form, or doped form, the product of electron density and hole density always is equal to intrinsic density squared. So in pure form, we know that n and p are equal. So n times p should be Ni squared, right? But it is also observed that in doped silicon, if you increase electron density, the hole density will decrease in such a portion that their product n times p will always remain Ni squared. Or in p-type doping, you increase the hole density p, the electron density will decrease in such proportion that their product will remain equal to Ni squared, and this observation and this relation between electron and hole density product at any condition equal to Ni squared, it is called mass action law. It is a very popular and useful equation in semiconductor device physics. So we already defined those. Doping is the process of mixing impurity atoms or foreign atoms in pure silicon to increase carrier density, electron density, or hole density. Dopant is those foreign material which will be mixed with the silicon to increase the charge. So doping is the process of mixing foreign material or impurity into silicon to increase the charge density, and dopant is the material that is going to be mixed with silicon, that is called dopant. Dopant can be of two types. Some dopant will contribute more electron, some dopant will contribute more holes. So if any foreign atom or dopant donates electron, it's called donor. If so, the number of donor atoms that will contribute free electrons to the semiconductor sample per cubic area is called donor density. So each donor atom can contribute one free electron. So if you want extra 1000 free electron per cubic volume, you have to add extra 1000 dopant atom into the sample. So donor density is the density of foreign atoms or donor atoms that should be mixed with the silicon sample to produce extra free electron. According to mass action law, density of electron and density of hole at any given point should be equal to Ni square. So when we add donor atoms to the silicon sample, what do we get? We get N-type semiconductor because each donor will donate one electron to the silicon sample. So by mixing donor atom with silicon sample, we get N-type semiconductor because each donor will contribute one extra electron. So the donor density is denoted by Nd. Nd means this number of donor atoms will be mixed per unit volume. So this number of extra electron will be added to the silicon sample. In its pure form, how many silicon electrons were there? Ni, intrinsic density, is the density of charge carrier in its pure form. So when I convert this silicon into N-type, electron density in an N-type semiconductor would be the electron it had in its pure form plus the electron you added. Typically, this donor density, required donor density to produce any useful N-type semiconductor is in the range of 10 to the power 17 to 10 to the power 19. So it's like a billion times larger than intrinsic density. So we can reasonably say that electron density in N-type semiconductor will be almost equal to donor density because the number of electron in its pure form, this number is negligibly small compared to this number. Why I am drawing this conclusion? Because you as the device engineer, you can determine the approximate 99% accurate number of free electron in your sample based on the amount of donor you mixed during the process. Or if you get that data, you know exactly how many free electron will be available. And we know that according to mass action law, the electron density in an N-type semiconductor sample times hole density in an N-type semiconductor sample, this product should be equal to always intrinsic square, mass action law. But electron density, we know that it is almost equal to donor density, but we do not know what is the hole density in an N-type semiconductor, but we can calculate it using mass action law. So hole density in N-type will be Ni square divided by Nd per cubic centimeter. Similarly, we can do the other one. Now the second type of dopant is called acceptor. So dopant is the material we use either to generate more free electron or generate hole. How do you generate hole? Hole is a virtual component. You have to take away electron out of the silicon sample. Then you create a hole in silicon sample, right? So the acceptor atoms are those material atoms that can take away an electron from the silicon, thereby it will produce a hole inside the silicon, a virtual product. So acceptor atoms, each acceptor atoms will accept an electron and produce a hole in silicon. So acceptor density is denoted by Na. Typically in any reasonable, so by mixing acceptor atom with pure silicon, what type of silicon we get? P-type silicon. Because by mixing acceptor atoms with silicon, we produce more holes, that means more positive particle, so it becomes p-type semiconductor. Typically, acceptor atom densities is in the range of 10 to the 14 to 19, which still is a very large number compared to intrinsic density. So we can reasonably guess that hole density in p-type semiconductor will be equal to the acceptor density. Now if we apply mass action law, we can get electron density in p-type from the mass action law. So these two relations will be used to calculate some basic electrical properties. They are not 100% accurate, but with reasonable accuracy, these two relations here will be used for calculating some electrical property in the later part of this lecture. However, from this discussion, what we get? By doping, we get two types of semiconductor. N-type semiconductor, by generating more electrons. P-type semiconductor, by contributing more holes. So, and in any semiconductor, conduction will be due to flow of electron and flow of holes. However, in N-type semiconductor, there will be more electron, less hole. In P-type semiconductor, there will be more hole and less number of electron. So that's why for N-type semiconductor, electron is known as majority carrier. Hole is known as minority carrier, because major portion of current or electricity in N-type semiconductor will be carried by electron. Smaller portion of the current will be carried by hole. In P-type, it's opposite. Hole is the majority carrier, electron is the minority carrier. Now, from this material property, how do we calculate some electrical property of different material sample? So, why we are doing the doping of semiconductor? Because we want to have some conductivity. In its pure form, it is not a good conductor, very poor conductor, but we want to use it as a transistor. When it is on, we have to send some current to the semiconductor or transistor. So you want to increase conductivity. Now, let us now introduce the relation between conductivity and the doping density we just introduced. Conductivity, the symbol of conductivity is delta. This conductivity is equal to Q times mu n times n plus mu p times p. Here, Q is the charge of the charged particle. It is one negative Q or positive Q. One unit negative for electron, one unit positive for hole. Mu n and mu p, these are some fundamental property, constant property of electron and hole. It's called mobility. Let's say a middle-aged person like me, if you push me, probably I will run at a much slower speed than any one of you, because you guys are still in teenager or early 20s, right? So because you are more energetic, each one of you. So for the same force, different particle will move at different speed. That's called mobility, right? So electron and hole, they each one of them will have its own mobility for a certain voltage or a certain electrical excitation force, and that is a constant for a certain temperature in a certain material environment. So Q is a constant, it's a charge. Mu n and mu p, these are two constants related to electron and hole. So what are the variable? Electron density n and hole density p. So now, device engineering, by doing device engineering, you can play with the electron density and hole density to achieve certain conductivity in your silicon sample. So that relation is showing conductivity is equal to Q times mu n times mu p plus mu p times, so Q n, mu n times n, mu p times p. Now mobility, as I said, it is a constant parameter, material property of a particular particle, how mobile it is. And then resistivity of any conducting material is what? Inverse of conductivity. So the resistivity, why we need resistivity? Because we need to calculate voltage drop, ohmic law, current, power consumption, we need resistance. I square R is the power consumption, because that will give us how much heat is generating. So resistivity is what? 1 over conductivity. So resistivity rho is 1 over sigma. So this is, if we calculate conductivity, we can calculate resistivity. Typically, in room temperature, in pure silicon, electron mobility is 1360. It's a constant term, it's a relative term. Mu p is 480. As you can see, mobility of electron is almost 3 times as high as mobility of hole. And resistivity is this, and sorry, conductivity of silicon in pure form is this, and this is 1 over conductive resistivity, yes.
So if electron mobility is much higher, and we are trying to integrate them into a CMOS circuit, because I remember from semiconductors that we preferred N types generally because of that electron mobility. So how do we compensate for that in a CMOS?
So that's why. So for signal robustness, we need to have CMOS. NMOS for producing 0, PMOS for producing 1. But you are absolutely right. Because since electron mobility is higher, NMOS transistor in general much faster. 3 times faster than PMOS transistor. That's why in any CMOS circuit, the NMOS to PMOS size is 1:3 at least. 1:2, 1:3. Why? If you, size means you make them wider, so that wider it is, lesser resistivity. If you make them equal size, then this one will be 2 to 3 times faster than this one. To make its conductivity larger, resistivity lower, we make it wider. So that's why in any CMOS circuit, NMOS block will consume about 1/3 of the area of the PMOS block.
Okay.
So it is a standard to make all the PMOS transistor 2 to 3 times larger than the NMOS transistor because of this mobility difference.
Can you explain it again, like why this mobility difference is making?
It's a good question. Why? The question is why mobility is higher in electron, or why higher mobility enables us to make NMOS to be smaller?
Yeah.
Okay. So first, actually, let me answer both. Why electron mobility is high? Electron is a real particle. As soon as you push it out of the orbit, it's free to move. On the other hand, hole is nothing but an empty space. So you have to basically, to move an empty space from one atom to next atom, you have to interchange it with another electron, right? Mm-hmm. So that is actually more energy consuming, more difficult. So that's why hole mobility is moving from one atomic orbit to the next atomic orbit. So it is less mobile. On the other hand, an electron, as soon as it's free, it is in the interstellar space between atoms, so it can easily flow. So its mobility higher. Now the question is, if the mobility is higher for any particle, it gives us higher conductivity.
Yeah.
Means it gives us lower resistivity. So resistance R is what? Resistance R is rho L by A, cross section. Cross section is W, whatever it is, like 2 dimension. So now I want to make NMOS and PMOS resistance equal or conductance equal, so that I don't have a bottleneck. Through NMOS it is moving very fast, and then PMOS has lower mobility, it becomes slower. But I want to make sure that signal passes through NMOS and PMOS at equal speed. So I have to have equal conductivity on the both sides. While to have equal conductivity means equal resistance, then I have to make it 3 times wider, because this is
Inversely,
the denominator, inverse.
Inversely
Proportional to the width.
Width, yes.
Length is constant because it's channel to channel. Length is constant for any technology. If it is a 18 nanometer technology, every transistor will be 18 nanometer long. Width or the size is what you can vary as the VLSI engineer. So to make NMOS resistance and PMOS resistance or conductance equal, I have to make it 3 times wider. That's why typically in any CMOS design, to make a uniform design between NMOS and PMOS taking same speed, I have to make PMOS 2 to 3 times wider. And that ratio will be determined by their mobility.
For the mobility of n-type electron is directly proportional to its mass. So mass of the electron is very much lower than the mass of the proton. That's why there is a difference.
No, there is a proton. It's a hole is not proton. Hole is an absence of electron. It's an empty spot in the orbit. So you are basically let's say this chair is empty. Now I want to create a hole here, so I have to move actually this 2% this way to create another hole here. So it's more energy consuming. But if I am sitting here freely as a free electron, I can roam around this room much faster, right? If I'm standing as a free, not like attached to any spot. So that's that's why the electron mobility, because it's a real particle, it's free to move. As long as you apply a positive volt, it will move in that direction.
Because we actually have to move it out of the band.
Yeah.
Right. Okay, so that's where that energy
So
comes
because you have to move it out of the band from one atom, kind of create the hole to the next atom. Hole is moving in this direction, electron is moving in this direction. So that's basically why hole mobility is always lower. So now some other related term before we start MOSFET. To force current in any direction through any semiconductor sample or metallic conductor, you need to apply voltage. What voltage does is applies an electrical field onto the carrier. That electrical field forces the carrier to move in one direction or the other. So how do we calculate the electrical field? Electrical field is nothing but voltage applied per unit length of the conductor or material. If the semiconductor or conductor sample is of the length D, if we apply a voltage V across the semiconductor sample, electrical field will be V divided by D, voltage per unit distance. Just quick recap of the basic electrical law. Now, if you apply a voltage V across a sample, how much current you will get due to the electrical field? It will be determined by the resistance, Ohm's law, V divided by R. And how do we calculate R? We calculate R, resistivity, we calculated previously. D is the length, WT, the cross-sectional area, width and thickness. So now, from this observation relation, what is the conclusion we get? Resistance is proportional to the length, resistance is inversely proportional width and the thickness or cross-section. It is proportional to the resistivity. Resistivity is a material property of any material. Now, let me introduce definition of diode. All of you know, but still, just a quick recap so that everyone is in the same. So, from all this initial discussion up to previous slide number 11, what is the conclusion? In a real semiconductor application, we use 2 types of semiconductor, P-type and N-type. When P-type semiconductor has more positive particle, N-type semiconductor has more negative particle electron. If we form a junction between a p-type and n-type semiconductor, this junction of two different types of semiconductor is known as a diode. One side of the junction will have high concentration of negative electron, the other side will have high concentration of positive hole. So when a junction is formed, across this junction, one side you have high concentration of positive particle, the other side you have high concentration of negative particle. So a physical phenomena called diffusion will take place as soon as we form a p-n junction, also known as diode. So typically, it is a property of any atom or any particle, things will diffuse from high density side to the low density side. That means some electron from this side due to higher density will move to this side. Some hole from this side due to high density will move from this side. So initially, diffusion of electron from n side to p side, diffusion of hole from p side to n side will take place for certain time. But after certain time, what happens? A negative electron, when it crosses this way, this side, immediately this side has lots of atoms with hole. Hole is what? An absence of electron, a gap. As soon as it finds a free electron, it captures it and it becomes neutron. Similarly, and if we move lots of electron, so this layer will have accumulation of electron. So at one point, it will become negatively ionized because movement of lots of electrons. Similarly, from this side, initially some electron will neutralize this layer first, and then more additional hole come here and it will become a positively ionized. When you achieve certain strength of positive layer here, what do we know? Positive charge will repel positive charge. So this positive layer, when it achieves certain strength, it will repel additional hole to cross. This negative charge layer, when it becomes strong enough, it will repel this negative electron to cross. So we will achieve an equilibrium. Initially, diffusion will take place from n side to p side to n side. Electron will cross from n side to p side, hole will cross from p side to n side. This side will become negatively charged on the p side, this side will become, and then further movement of electron and hole will be stopped. And the formation of this ionized charge layer is called, this ionized layer is called barrier or depletion layer. Because why it is called depletion layer? All the free electron from this area move from here to here. All the holes from this area move from here to here. They are depleted from any available charge carrier, but in the process, one side became positive, the other side became negatively ionized. So across it, a voltage has formed. That is called barrier potential, VD or VT, and this is called voltage barrier. So this is a common phenomenon. When a p-n junction is formed, that is a p-type semiconductor and n-type semiconductor is connected together, a junction is formed, hole will flow in this direction, electron will flow in this direction, a barrier will be formed here. This is the symbol of diode. It shows that electricity direction is direction. Why? If electron flows in this direction, we assume that the positive electron direction is opposite direction, and that is what is happening. Positive hole is flowing in this direction, negative electron is flowing in this direction. So the electricity direction is from A to B, so that's why the symbol has an arrow towards B. This is P side, this is N side. So the initial phenomena, when from high density side electron moves from N side to P side, and from high density hole, from P side to N side, that movement is called diffusion. It is the movement across the junction due to the variation in density. And then at one point, one side become positively ionized, one side become negatively ionized. Positive charge will attract some electron, negative charge will attract some hole. There will be some movement that is called drift due to the push and pull of opposite polarity. But at equilibrium, the junction, the barrier will come at a steady state, it will no longer expand beyond that junction region. That's when diffusion and drift will come at equilibrium. But in the process, it will create a junction with N-type layer, negative layer on the P side, positive layer on the N side, and the resulting voltage across the junction is called barrier potential or junction potential. It is a very, very important parameter for diode. So, as I said, across the PN junction there is a depletion layer formed, and across the depletion layer a barrier potential is formed. The positive terminal of the barrier potential or junction voltage is on the N side, negative side will be, negative terminal will be on the P side. So N side is positive, P side is negative. This difference is called barrier potential. So now, what would be the magnitude of that barrier potential? The magnitude of the barrier potential across a PN junction can be calculated by this formula. It is also known as built-in potential. As soon as a PN junction is formed, by default, there will be a barrier formed, and across the barrier, a potential or a voltage will arise. That voltage is called barrier potential, built-in potential, or junction potential. And its magnitude is given by this. This is called thermal potential, KT over Q, a constant. K is the Boltzmann constant, T is room temperature, Q is electron charge. So at room temperature, T is equal to 300 degree Kelvin. What is this? This is acceptor density on the P side, this is the donor density on the N side, and this is intrinsic density. So this formula will give us the magnitude of the barrier potential or built-in potential that will be arising due to the formation of PN junction. And Boltzmann constant is a constant, electron dense charge also is a constant. So we'll be using this formula also for doing some numerical calculation for diode. So, due to the formation of this barrier and barrier potential, a PN junction diode under normal condition cannot carry current. Why? To carry current, if you apply a voltage here, this positive side will repel any positive particle from crossing from P to N side. This negative layer will repel any negative electron from crossing from N side to P side. If electron and hole cannot cross or cannot flow, there is no current. So a PN junction diode in its pure form, due to the presence of this barrier potential, cannot carry a current. That's why diode under normal state without any application of the voltage is considered as an off device. Why? Because it cannot carry any current. However, if we want to utilize this diode or semiconductor device in a real integrated circuit, sometimes we have to turn it on, sometimes we have to keep it off. To turn it on, we have to apply voltage in such a direction so that we can basically suppress or eliminate the barrier so that current electron can flow. That process is called forward biasing. We are applying a voltage in a way that the barrier will be eliminated, electron and current can flow freely through the diode. that is the on state of the diode, and the process of applying voltage to eliminate the barrier is called forward biasing. But if we apply a voltage in the direction that will further increase the strength of the barrier to turn the device off, strongly off, we call it reverse bias. So, for forward bias, we have to connect positive terminal of the battery to the P side, negative terminal of the battery to the N side. For reverse bias, we have to connect negative terminal of the battery to the P side, positive terminal of the battery to the N side. So this is called forward bias. How forward bias will eliminate the barrier to complete the current path, to flow current here? What is the battery positive terminal? It has more positive particle. So it will, as soon as you connect it, so it will inject positive particle into the P region. So positive particle will travel, however, it will see a negative layer here, right? Negative layer means there are more electrons. So it is injecting positive particle. So those positive particle will mix with those negative ion and you will neutralize it. When you neutralize it, this negative layer will be gone. Similarly, from the negative battery terminal means it has more electron, more negative charge. It will be injected into N side. So those electrons will be injected. As it moves, it will see there is a positive layer. This positive layer will attract those electrons. They will merge and it will become neutral. So the barrier will be gone beyond certain positive voltage. So reverse bias will turn on the device by eliminating the barrier. On the other hand, if I connect negative terminal with the P, more electron will attract hole. So it will take away more positive particle out of the P-type side. This side is positive, it will attract electron. It will take more electron out of the N-type, so this barrier will spread. Because by losing electrons, so it will become strongly off. So to turn on a diode, we have to forward bias it. Forward bias means connecting positive terminal of the battery with P-type. Easy to remember. Positive terminal to P-type, negative terminal to N-type. Forward bias, the transistor, it will turn on. Opposite with reverse bias, it will turn it off.
The process is happening forward and reverse after the diffusion process, right? So
Yeah. So no matter, whenever a diode is created, by default this barrier will be there. Even if you do not apply any reverse bias, by default the barrier is there. By default, as soon as a PN junction is manufactured, it is in off state. So to turn it on, only way you can turn it on by applying forward bias. But if this is a real signal, it is a positive negative voltage, like a pulse signal train. So sometimes it will be positive, sometimes it will be negative. If you apply reverse bias, its off state will strengthen, so it will not carry any current. But by default, any diode is in off state, even if you do not apply any bias.
Like in reverse bias, after this diffusion condition, it always this P-type will have a negative charges also, right?
Yeah.
So that negative voltage will ripple the.
Yeah. So here it is negative electron, so it will basically take away more hole out of this area. So this depletion layer will actually spread. It will become, because more and more layer will be losing holes.
They were combining.
Overall, it's charge neutral. But by losing more and more hole, this layer will expand. Here, by losing more electron, this layer also will expand. So the barrier will expand and it will enter into stronger off state. So whether it's in reverse bias condition or forward bias condition, at any given point, the current that will flow through any diode can be calculated by a very famous diode equation. It's called diode current I equal to Is times e to the power Vd divided by pi t minus 1. This one we already calculated in the previous slide, variant potential. This is the bias voltage you apply. For forward bias, it's a positive voltage. For reverse bias, it's a negative voltage. And this is also a material constant. It's called reverse saturation current. It is a function of the material and diode physical dimension. So diode current, both in the reverse bias condition or in the forward bias condition, can be given by this famous diode model or diode current, ideal diode current equation. In the reverse bias, this current will be very, very small or negligibly small, close to zero. So diode is considered in off state. In the forward bias condition, initially current will be zero, but as soon as you eliminate the barrier, the current will increase exponentially. So derivation of this diode equation or derivation of this barrier potential equation, these are subject to basic electronic class or semiconductor device physics class. So we will not actually go through those. We will take this equation as it is. If there is any question in the exam that needed this equation, the equation will be actually printed on the cheat sheet. So don't worry about memorizing this equation. So I am just recapping some basic semiconductor physics material to establish the foundation for MOSFET. So this is a problem I want each one of you to practice at home, because the homework problem and some exam problem will be exactly like this, utilizing the formulas we have discussed. So this formula as well as these two formula. This one, in some problem you have to utilize this one, in some problem you have to utilize this one. Just practice this problem at home. Just application of the formulas we have learned so far. Now we are starting field effect transistor and MOSFET. Okay. Huh?
It is time.
It is time? Okay. Yeah.
You did all that build up.
Well, there are lots of material to cover. So anyway, so I'm still on track. So we can finish all the material. Typically, I finish module 2 at the end of